Today I'm presenting April, Attention Privileged Reinforcement Learning. This work was conducted between the A2I laboratory and DeepMind. Image-based reinforcement learning is an appealing framework due to the generality and accessibility of the observation space across domains and platforms. However, visual RL suffers from poor sample efficiency, robustness to environmental variations, and generalization to extrapolated domains. Consider JCoReach, a domain introduced in this work, where the task is to reach the diamond-shaped object, here on the left, in the presence of distractors. Suppose we wish to become invariant to environmental changes that may be encountered during deployment, such as the camera angle and textures. Traditional visual RL would not be robust to such changes. Visual domain randomization adds robustness by randomizing visuals during training with the aim to hopefully cover all variable aspects of the environment that may be encountered. Unfortunately, works have shown that the increased variability of the training domain can decrease learning rates and hurt asymptotic performance. Furthermore, it is often not feasible to cover all variations that may be encountered. How could one generalize to task-independent variations, such as test time domains with increased clutter? Attention-privileged reinforcement learning leverages privileged information available during training but not deployment, such as environmental states for sim-to-real transfer, to not only increase training performance during randomization, but to also improve generalization to domains with increased distractors. April achieves this by training two attention-augmented actor-critic agents, one symmetric and state-based, the other asymmetric and image-based. Efficient image-based learning is achieved by sharing experiences and aligning attention between both agents. In this way, the image-based learner bootstraps off efficient exploration achieved by the state space agent and quickly learns to suppress highly varying parts of the image domain that are task irrelevant, which in turn simplifies the observation space. Here we see an example of the learnt image-based policy on a training domain. Notice that April has learnt to suppress the task-independent aspects of the observation space, such as the distractor objects and the background. Thanks to April's efficient form of knowledge transfer, its learning rate and asymptotic performance is greater than all baselines we compare against, specifically asymmetric and symmetric actor-critic, and a variant that learns an observation to state space mapping. When we deploy April to test time domains with increased clutter, April's attention module generalizes favorably, suppresses the additional distractors, and therefore continues to solve the task. When we compare against the baselines without attention, we see that April generalizes far better to domains with increasing levels of clutter. Specifically, April is comprised of three modules. The symmetric actor-critic module AS efficiently learns a state-based policy which is unaffected by visual randomization. During training, the attention module efficiently learns which aspects of the environment are task relevant. The attention alignment module AT then converts state attention to image attention to achieve efficient knowledge transfer between agents. This is done using privileged information commonly available in simulation. First, state attention is converted to object level attention using state mapping matrix M, and this is then converted to image attention by using object level segmentation maps Z. The final asymmetric actor-critic module A0 efficiently learns an image-based policy by aligning its attention with the target attention from AT and by sharing a replay buffer with the state space agent. We evaluated April across three domains. Both Navod and JCoReach are reaching domains with clutter. For Walker 2D there is no clutter, but learning is still difficult due to visual randomization. The learning curves on the top right demonstrate that April strongly outperforms all baselines during training, except for Walker 2D, where it matches the observation state mapping baseline. We then evaluated each method on unseen held-out domains with increased clutter. As seen in the bottom right, April's generalization ability far exceeds that of the baselines, which the ablations show is thanks to its attention module. When visualizing April's attention maps, it is clear that it's the attention module that leads to successful generalization. On the extrapolated domains, April correctly suppresses the additional distractors, which in turn leads to strong generalization capabilities. In contrast, both baselines without attention exhibit poor generalization and are unable to complete the tasks. In conclusion, attention-privileged reinforcement learning leverages privileged information via aligning attention masks and a shared replay buffer in order to efficiently learn an image policy despite visual randomization and increase robustness and generalization to held-out domains via its attention.